Hello everybody. Let us discuss about complexity theory of solving problems. Now, complexity theory classifies problems by how much time or memory they need as the input size grows. The philosophy behind complexity theory is to understand how difficult problems really are and what limits exist for computation. Complexity theory is a way to measure the power of algorithms and machines by asking how much time and memory are needed to solve a problem as the input size grows. Now, the motivation behind the complexity theory is both theoretical and practical, meaning by theoretically, it helps classify problems into categories of solvability and efficiency, thereby guiding research on whether faster algorithms are possible or not. And practically, it tells us when to stop searching for an exact solution and use approximations or heuristics instead. For example, optimization problems exist, and the optimization problems like scheduling, routing, protein folding, these are all NP hard problems. Knowing this helps scientists focus on near optimal solutions instead of wasting resources on impossible solutions. Now, let us try to understand what are the types of problems that the computers need to solve and how we can identify and classify these different problems into different categories. So let us try to understand this concept of complexity theory. So there are various types of problems for which the complexity can be estimated. The first type of problems I discuss in this lecture is the problems which are known as tractable problems. Problems for which running time grows polynomially with the size of the input. This word polynomial is very important. There are two ways to discuss the complexity. One is the polynomial way and the other is the exponential way. Roughly speaking, polynomial way is a better way and exponential way is a little harder way and complex way. If the complexity can be expressed in terms of polynomials, then the complexity is termed as less, whereas if it is raised to the exponential power, if it is, the input, let us say the input is defined as n. Let me just explain here. Let's say the input is defined as n. If this input n exists as a power of a base, like for example 2 raised to the power n and so on. So this is exponential. If the input, which is let's say n, and it has got certain power k, this is polynomial, right? So this categorization we have to understand. Now, I was discussing about the tractable problems for which running time grows polynomially with the size of the input. Now, formally, if a problem can be solved in, see here, this is the input size n raised to the power k. So this is polynomial order O, big O of some polynomial factor. These can be solved in time for polynomial time for some constant k. K is constant, it may be 2, 3, 4, but still it remains the polynomial complexity. Then these are called tractable problems. Now, tractable problems correspond to the P class of problems. What are these problems? for which the running time grows polynomially with the size of the input. These problems are solvable in polynomial time by a deterministic Turing machine. Now, what can be termed as a Turing machine? It's a standard model of computation that defines the meaning for algorithmically solvable, right? And what is the meaning of deterministic? Because at any given time the machine has exactly one possible action to take. So that is deterministic. The action, we know what action can be taken. So therefore it is a kind of deterministic action through that machine. Now there are second type of problems known as intractable problems. Now problems for which there is no known polynomial time algorithm for solving all instances of the problem. Intractable problems require super polynomial or exponential time. So as I just said, if the input size is acting as an exponent, so therefore it is exponential. N factorial is a kind of super polynomial, and so on. So that means if some problem is having time complexity expressed in terms of big O of some exponential power, then this is a complex solution available. Now in simple terms, as the input grows, the running time explodes too fast to be practical because it is exponential in nature. Intractable problems usually fall into NP class of problems. So there are two classes that we have just discussed. One is P class of problems, polynomial time solvability, and the other is the NP class of problems, which are exponential in nature. The time complexity cannot be expressed as a polynomial time. Now there are two more types of problems that I would like to discuss here. One is the optimization problems. Now an optimization problem is the one which asks, what is the optimal solution to the problem X? What is the best solution or the optimal solution to a certain problem X? And the goal of this task is to find the best solution from all let us say there exists some possible solutions. Now what is the best solution available? We have to find that best solution. So that is this type of problem is categorized under optimization problems. The goal is to find the best solution from all the possible solutions according to some objective function. We have to define the objective function. Based on that objective function, we have to find the best solution out of all possible solutions. So X star is the best solution. So if there is a function fx and fx has got capital S solutions, now this minimum means the minimum energy solution. So X star is the minimum energy solution. So this X star is the best solution, which corresponds to the minimization of the this function fx. That means we have to find out a solution for which the function is minimized in terms of maybe energy or any other parameter. So this is the objective function basically. Fx is the objective function for optimization. There is another type of category of problems, and these problems are known as decision problems. A decision problem is the one with yes or no answer. An optimization problem tries to find an optimal solution, as I have just discussed, whereas a decision problem tries to answer a yes or no question. A decision problem is a function f where sigma star is the set of all possible inputs or strings, and the output is only 1. The output is only 1 out of 0 or 1. That means it is a yes or no type of solution. So I have just discussed tractable problems, problems for which the running time grows polynomial with the size of the input. Intractable problems where the polynomial, there is no known polynomial time, but the intractable problems require exponential or super polynomial time. So these are categorized as the NP class of problems. Then optimization problems, we have to find the best solution out of a set of possible solutions based on according to some objective function. Then the decision problems, where the solution to the problem is a yes or no answer, and out of the set of all possible inputs. Then you apply all complete set of possible inputs and keep on asking that whether this is the correct answer or not. You will get the answer in yes or no, or 0 or 1 as output. Now let us now try to understand the problems that help determine or classify computational complexity. So as I just described previously, there is a class P type of problems which can be solved efficiently by a deterministic Turing machine. That is, these are solvable in big O of certain polynomial, where Pn is a polynomial on n. A deterministic algorithm always computes the correct answer. Class NP type of problems, NP means non-deterministic polynomial time. Problems for which a given solution, this is important to understand here, problems for which if the solution of the problem is given, that's what I am trying to say here, problems for which a given solution, that means the solution is given to you. You are not to find the solution. Problems for which the solution is given, but you have to verify this solution. Problems for which a given solution can be verified efficiently in polynomial time. Efficiently means in polynomial time. So the solution is given, you have not to find the ultimate solution, you have to only verify the solution. If the verification can be done in polynomial time, we will categorize it as class NP type of problems. Even if finding that solution might be hard, even if you are not able to find the solution, but given a certain solution, if you are able to verify it in polynomial time, this is NP class of problem. Now the solution can be checked quickly, but not necessarily found quickly. More precisely, NP is a class of decision problems. So basically we will this NP class of problems we will attach to the decision type of problems, more specifically or more precisely. More precisely, NP is a class of decision problems that are solvable in polynomial time on a non-deterministic machine. I just discussed what is a deterministic machine earlier. So let me just, so this is a deterministic machine. The machine has exactly one possible action to take and it will give an answer. A deterministic machine has got one possible solution and it will provide you the answer. That means the solution is determined. Solution is already determined and it is deterministic in nature. Whereas, what is a non-deterministic machine? We have to understand. A deterministic computer is what we know, but a non-deterministic computer is the one that can guess the right answer or solution. A non-deterministic machine will not exactly determine the solution, but we will try to make a guesswork that this might be the solution, or this may be the solution which can be found in future. At that time you are not sure about the solution, but you are guessing the solution in the belief that in future maybe this is the solution. So think of non-deterministic computer as a parallel machine that can freely spawn an infinite number of processes. Now NP is a class of problems whose solutions can be verified in polynomial time. Now there is always a debate that goes on in the computing community, and that debate is P versus NP. Whether there is a very thin line between P and NP, whether P is equal, whether P can be equal to NP or not. This is a central question in computer science. Is every problem whose solution can be verified quickly also, because NP means verification of the solution is possible in polynomial time. Now whether that is solvable in polynomial time or not, if it is solvable, it will become P. So that means, can NP merge with P or not? Can NP can NP be equal to P or not? This is the millennium question, $1 million question. That's what there is. This is one of the 7 millennium prize problems worth $1 million. So that means we have to find out if P is equal to NP, then all NP problems become tractable, right? If P is not equal to NP, then NP complete problem. I will come to what is NP complete and NP hard in just a moment. So P type of problems are a subset of the NP type of problems. Now as examples, we can say that P type of problems are like sorting, finding Dijkstra's algorithm, matrix multiplication, finding the greatest common divisor using the Euclidean algorithm, and this is primality testing using the AKS algorithm. And the NP class of problems may involve Boolean satisfiability. This is the first problem which was actually put in the category of NP. Hamiltonian cycles, knapsack problem, graph coloring, Sudoku problem. So easy to check. Sudoku means it is easy to check, it is easy to verify, but hard to find the solution, actual solution. So we have tried to understand what is P and NP. Now with NP there are two more characteristics attached, and these are class NP hard problems. So let us see what is NP hard. A lot of times you can solve a problem by reducing. So what happens is, you are given a problem, maybe solving that problem straight away may not be the viable solution, but what you can do is, you can solve this problem by reducing it to a different problem. But we know the solution to that different problem. Original problem is reduced to a different problem. Say I can reduce a problem B to problem A, and if the solution to problem A is given, that means for the problem which we are trying to find a solution, what we do, that we reduce that problem to another problem, and we know the solution to that another problem. And if that is the case, we will say that we can find out the solution of the original problem. So if the solution to problem A, that means we can reduce a problem B to problem A. If the solution to problem A is given or known, therefore I can easily construct the solution to problem B. Easily means in polynomial time. Now a problem is NP hard. So what is NP hard in that case? If all problems in NP, so NP means all problems are not solvable in polynomial time but verifiable in polynomial time. So that is the NP class. If all the problems which exist in the NP class, right, can be mapped to another problem, right, so that another problem will be called as NP hard. Now a problem is NP hard if all the problems in NP are polynomial time reducible to it. So a problem is NP hard if certain problem X is NP hard if the set of all the NP problems can be reduced in polynomial time to x. All the problems in NP are reducible to x in polynomial time, then that x problem is known as NP hard. Every problem in NP is reducible to this Hamiltonian cycle as an example. That means every problem that exists in the NP class can be reduced to the Hamiltonian cycle. So therefore Hamiltonian cycle is an NP hard problem. For example, TSP in NP class is reducible to Hamiltonian cycle. Now there is another categorization which is known as NP complete. Now a problem is NP complete if the problem is both NP hard also and NP also. The difference between NP and NP hard is there are certain, let us say there are 10 problems in NP. But all these 10 problems are reducible to 11th problem, right, in polynomial time. And we know the solution of this 11th problem. So therefore, this 11th problem is known as the NP hard problem. But NP complete will include all the NP hard problems and NP problems. So if you can solve one NP, that is NP complete. If you can solve one NP complete problem in polynomial time, you can solve all NP problems in polynomial time. For example, TSP decision problem version, click a problem, vertex cover, graph coloring, all these are NP complete problems. So these categorization is to be very clearly understood. NP hard problems are at least as hard as NP complete. At least as hard as NP complete, but may not be even in NP. So that cannot be in NP class, but NP hard problems are at least as hard as NP complete. That is, verification might not be efficient or even possible. So at least as hard as NP complete, maybe even harder. This is, I am talking about the NP hard problems. So NP hard problems are at least as hard as NP complete, but maybe more harder than NP complete. Now let us see what is reduction. A problem R can be reduced to another problem Q if any instance of R can be rephrased to an instance of Q. That means R is reducible to Q. This is how we express when R is polynomial time reducible to Q. If R is polynomial time reducible to Q, we denote it like this. So if all the problems R belong to NP are polynomial time reducible to Q, then Q is NP hard, as I was just trying to explain. And we say Q is NP complete if Q is NP hard and Q also belongs to the NP class. So if R is polynomial time reducible to Q and R is NP hard, Q is also NP hard. These are certain quick decisions we can try to understand about the classification or the classes of P, NP, NP hard and NP complete type of problems. So this is a Venn diagram for P class of problems. This is a P class. There is an overall NP class and P class lies in between. So when P is equal to NP or P is not equal to NP, so that's the millennium question I was just trying to mention. And I have specified certain problems which belong to P class, like path problem, NP problems like graph isomorphism, and this, let's say this is NP hard, because NP hard, there is a class NP hard. Some problems in NP hard may not be NP, may not belong to the NP class, but all problems in NP class must be reducible to a problem must be reducible to one problem. So that problem will be called as the NP hard. So if a problem is NP hard also and NP also, so this intersection belongs to the NP complete. Now there is another class which is based on the memory or the space as a parameter. So problems which are solvable using polynomial space, which is space basically means memory. Even if they might be they might take exponential time, even if the running time of that problem is exponential time, but they are taking a space which is polynomial in nature as the input size grows. So memory is limited, but time can be huge. Quantified Boolean ledger. So these are certain examples of the planning problems in artificial intelligence. As I said, these are certain problems uh, which can be put in the category of P space. Now there is another class that has been added due to the quantum computing concepts, in which, because quantum computing redefines this boundary of P and NP by solving certain hard problems faster. So what does quantum computing do? Quantum computing, using the quantum computer, we can solve these hard problems in polynomial time. Quantum computing redefines this boundary by solving certain hard problems faster, showing that computational difficulty depends not just on the problem itself, but on the model of computation used to solve it. So therefore, what happens is that the quantum computing using the quantum computer, it is possible to solve it is possible to solve an exponential time complexity problem in a polynomial time complexity using quantum approach. So that class is known as BQP. For example, the Shor's algorithm. Shor's algorithm is related to prime factorization, in which it is not possible to find the factors of a composite number, large composite number, but using the quantum approach, we will be able to find the factors of the composite number in polynomial time. Grover's search algorithm, using the quantum approach, we can do this this type of search, which is it's unstructured database is there, so we have to search for a particular item. So Grover's algorithm using the quantum approach can do it much faster. Quantum simulation is the other. So we can we can place these subsets like P space. This P is a subset of BQP is a subset of P space. And where does NP and BQP are related to each other? It is not sure in this present computing world whether NP is a subset of BQP or BQP is a subset of NP. So this is all about the complexity issues. These are important to understand as far as the quantum algorithms, or in a way any classical algorithms are concerned, because we have to specify the complexity levels in terms of these. We have to categorize these algorithms. We have to categorize algorithms in these classes, so that quickly one should know the complexity levels of that algorithm. Thank you.